We're going to take a peek at our homework from last night, page 592. We got a bunch of questions we want to go over here. 10, 12, 13, 14, 15, and 16. We'll start at question number 10. It says, list at least 2 differences and 2 similarities between gravitational and electric fields, gravitational and magnetic fields, and electric and magnetic fields. We know that they have a lot in common, right? And we've drawn a lot of connections between the 3 of those fields over the last 2 units. Okay, let's specify now a couple of similarities and a couple of differences between all 3 of those fields. Give me a similarity, difference, whatever, between an electric and a gravitational field. What's one thing they have in common or one thing that they don't have in common? Good. They both have an inverse square relationship. That's something they have in common. In fact, although we don't have an equation for the magnetic field, you would find the same deal with the magnetic field as well. That would be something that they would have in common as well. You just wouldn't know that because we haven't done an equation for that. All right, good. There's one similarity. What's another similarity or difference between any of these fields? I don't care whether you're doing question A, B, or C here. How about a difference? I got one. Gravitational fields always have to point toward the producer, right? They can never point away from the producer because mass always produces a field acting towards it. Whereas an electric field can point toward or away from the producer, and a magnetic field can point toward or away from the producer, depending upon what type of producer you have. Okay, gravity, there's only one type of producer, it's mass. So it always points toward that. There's a difference between them. On that token, actually, we could consider that a similarity between electric and magnetic fields. They can be toward the producer or away from the producer. Both of them can be. Let's go back to electric and gravitational again for a second, because I just thought of another one. Remember when we started talking about electric forces and gravitational forces, electric fields and gravitational fields? Remember when we said that one is almost always stronger than the other one by a lot? You guys remember which one was stronger than the other one? Yeah. Yeah, the electric field is way stronger than the gravitational field. So that's a difference between the 2 of them as well. We've kind of gone all around the A, B, and C and similarities and differences, so I'm honestly not sure how many we've actually answered for these, but you get the idea of what we're talking about, right? Okay, whether you have 2 or 3, or even if you only have 1 for 1 or 2 of them, it's not the end of the world. Okay, the idea is to start thinking about, okay, what makes these things like each other? What makes these things different than each other, right? The next question was number 12. Why does dropping or heating a bar magnet decrease its magnetic properties? Well, first of all, what gives a bar magnet its magnetic properties? Not on a molecular level, or even smaller than a molecular level. We're not talking about the spins of electrons stuff that I talked about a little bit. I mean, that's true. That's ultimately what does give the magnet its magnetic effect, but we don't want to look at it in that much detail. You don't need to know that much detail. The detail to which we described it and drew a picture in class simply relates to the domains, right? Domains aligning in the same direction give a magnet its magnetic effect. So what do you think dropping the magnet's going to do to it then? Or heating it up for that matter? If these domains are all pointing or more or less pointing in the same direction, and I drop it, then I'm adding kinetic energy to the system, right? I drop it, it scrambles everything around. When you increase the kinetic energy of something, it tends to increase the disorder in stuff, right? If there's a lot of kinetic energy in this room, then people are going to start moving around a lot more. If there's more kinetic energy in this magnet, then the domains are going to start moving around more and become scrambled. So it literally scrambles the domains when you drop it or you heat it up. Next question, number 13. Consider a bar magnet and Earth as shown below. Describe the similarities and the differences of their magnetic fields. Well, I can think of one really big similarity, and I can think of one really big difference. Okay, the similarity that I'm thinking of relates to the shape. It doesn't look almost the same. If you twisted that bar magnet around so that it was almost vertical, doesn't it look remarkably like the magnetic field surrounding the Earth? It's like almost there's a bar magnet inside the Earth. The shape is the same and the direction is the same. Well, there's three properties of the magnetic field that I can think of: shape, direction, and the third one would be, and this is what's different about these two magnetic fields: shape, direction, and strength. Yeah, the strength of the magnetic field surrounding the bar magnet is quite a bit stronger than the magnetic field surrounding the Earth, right? Remember those numbers that we did one day in class? I said, don't memorize these numbers, but if you can kind of have a ballpark for the Earth's magnetic field and the magnetic field surrounding a bar magnet, just so you know if you're on the right track with the question. Around a bar magnet, it's usually in the range of 10 to the minus 2 Tesla. Around the Earth, it's usually in the range of 10 to the minus 5 Tesla. So a bar magnet has a magnetic field strength of somewhere in the range of 1,000 times stronger than the Earth's magnetic field. Same direction, same shape, but not the same strength. Bar magnet's almost always going to have a stronger field. 14. Why is it difficult to get an accurate bearing with a magnetic compass near the poles? I'll draw a picture of that first of all here. Here's the Earth. Here's the little pretend bar magnet inside the Earth. Here's the magnetic field surrounding that pretend bar magnet or surrounding the Earth. We have no problem whatsoever putting a compass right here. It's going to point in the direction of the magnetic field towards the South Pole, what we think of as the North Pole. But why can't we stand on the Earth here? Why can't a really tall person stand on the Earth there, holding a compass like this, and have it work? Yeah. Yeah, not so much because they intersect, because the reality is if they're intersecting, if there's more than one field in one place, then what happens is you get a net field. So it's not like you have to worry about all these different fields. It's the overall field caused by all the individual fields. So we're not going to worry so much about that. Yeah. Yes, if you're standing right up here at the South Pole, the needle would want to point down. But look, you're holding the compass like this. Remember the first day we started this unit? We had a compass that will go on two axes, right? It'll go that way or that axis, the x-axis or the y-axis. We needed to point on the z-axis here, right? We needed to point on the third axis right here, point down towards the Earth. Or if you're in Antarctica here, standing upside down, because that's what all the penguins in Antarctica do, right? They stand upside down on the Earth, stand on their heads. Then the compass is going to want to point outwards like this, but it can't unless you have a special kind of compass. It's a three-dimensional compass. You can't do that. It can only point horizontally parallel to the Earth. Number 15. Do magnetic field lines always run parallel to the surface of the Earth? Let's go back to our picture that we just drew. These field lines here are pretty close to parallel, right? Not perfect, but pretty close. What about the field lines up here? Are they parallel to the Earth's surface? Not even close. So the closer you get to the poles, the further away from being parallel they are. In fact, at the poles, the field lines are almost perpendicular to the Earth. They're closer to being perpendicular than they are to being parallel. So the answer to that question, the simple answer to that question is no. The field lines don't always run parallel to the Earth's surface. Although, over most of the Earth, you can see here that they do run not quite parallel, but almost parallel. And finally, number 16, my favorite of the questions here, and probably the hardest of the questions here. If a current-carrying wire is bent into a loop, why is the magnetic field stronger inside the loop than outside the loop? Does anybody think they have an answer to that question before I answer it? I talked about that with 3 or 4 people today at various points that asked me questions, and I can't remember if I briefly talked to 1 or 2 people from this class and some people from the other class as well about it. Now, I think you got an answer for that? Yeah, that's exactly it. And the word stacks actually works pretty well, I think, actually. If this is my, I'm going to roll a masking tape here somewhere. Here it is. This is my one single loop of wire here, okay? And you can see I've got the current drawn here. I got it drawn up in the front, although it doesn't matter. I could have made it down in the front. Doesn't really matter. Okay, current up in the front, and then you can see it goes down in the back. So it's going around like this. Okay, one single loop. Okay, one single loop. The effect gets magnified if I have 20 loops by a factor of 20. But let's look at one single loop here. We always use the coil rule to determine the polarity of this. So let's do that right now. Okay, coil rule says stick your fingers in the direction of the field, which is up in the front. Okay, so my fingers go in the front, point up. My thumb's going to point towards the right. That means in that case, when I have an electric current, whether you have something inside it, a core or not, current going up in the front, down in the back, I'm going to have a magnetic field pointing this way with a polarity of north and a polarity of south. Now, we don't use the wire grasp rule to determine the polarity of this coil, but we could. It's just a little bit more awkward to do it. I want to go back and use the wire grasp rule for a second. I want to do it in a couple of different spots. Okay, remember, wire grasp rule opposite to the coil rule. Thumb in the direction of the particle, fingers field. So I'm going to stick my thumb upwards here in the front, and I'm going to wrap my fingers around. So right here at this point, try to do this because I need about 3 hands. At this point, the magnetic field points this way. Inside the coil, the magnetic field would point that way. Exactly the way that we have it drawn there, right? Magnetic field points to the right. Let's do it in the back. Thumb points down in the back. Fingers outside point this way. Fingers inside point this way. You see what's just happened there? We've got a magnetic field caused by the wire in the front that's outside and inside the coil. We've got a magnetic field that's caused by the wire in the back that's outside and inside the coil. The magnetic fields that are outside the coil, well, one of them is here, one of them is here. The magnetic fields that are inside the coil are both inside, pointing in the same direction. So this wire caused a magnetic field inside pointing this way. This wire produced a magnetic field inside pointing this way. They stack upon each other, produce a stronger magnetic field. You mentioned a term earlier, Dom, constructive interference. It's like constructive interference. Remember with waves last year, constructive and destructive interference? Okay, you get two fields pointing in the same direction, they stack or they constructively interfere, whereas outside they don't. It's not like it's destructive interference on the outside. There's just nothing to interfere with, right? Okay, field outside, but inside you got a field caused by this part of the wire, a field caused by this part of the wire, and a field caused by every other part of the wire as well, stacking. Now you kind of talked about having more loops. You can imagine if you have 20 loops, what we just described is going to be magnified by a factor of 20, right? There's an equation that describes the strength of a solenoid, the strength of the magnetic field produced by a solenoid. And one of the factors, one of the variables that appears in that equation as a linear relationship with magnetic field strength is literally just the number of coils, the number of loops that you have. It's not a complicated thing. If you have 5 loops, okay, let's say you have 20 loops, and another one has 5 loops. The one that has 20 loops is going to be 4 times stronger than the one that has 5. Yep. All right, if those questions are good, let's just do, since we didn't actually have to do that in the do this in the practice questions that we had last night, let's just do another example of the coil rule to refresh our mind on that before we have our quiz tomorrow on the coil rule. Let's say we got a core here that's not magnetized. Although remember, you don't actually need to have the core. The effect is just more noticeable if you have the core, because the core essentially kind of stores the magnetic field. You got a soft iron core here, a core that's ferromagnetic material. We got a wire that's wrapped around that core that looks like this. And we've got a battery that's set up like this. What's the negative side of that battery, by the way? This side or this side? Yep. Yeah. The left side of the battery, the long side of the battery is always positive, and the short side of the battery is always negative. Now, if you want to use electron current, which we almost always use, then we would say the current goes counterclockwise here, up in the back, then down in the front, up in the back, down in the front, and so on. Now, if you wanted to use conventional current, you could, but it would go the other way, right? It would go clockwise instead of counterclockwise, up in the front, down in the back. It's going to give us the same answer. You just got to be careful to use your left hand for electron current and your right hand for conventional current. We'll go with electron current because that's the way your Alberta Education on your diploma exams almost always does. And that's good because that's the way I prefer it anyways. We take out our little arts and crafty thing that we made yesterday. We stick our fingers on the word front. Remember, you wrote the word front on it. Okay, we stick our fingers on the word front in the front, right? So down in the front. So put your fingertips, not your knuckles or the palm of your hand or whatever, your fingertips on the word front, pointing down. And then I grasp the coil, and my thumb will automatically point towards the left-hand side. So it's chase correctly identified. The magnetic field inside the coil is going to go that way. Chase doesn't have the little manipulative that we made yesterday in his hand, but he still managed to get it, right? Okay, I'm not saying that you have to do this. Okay, yesterday I made you do it. Okay, if you get this and you're able to kind of visualize it without actually creating this little manipulative, go ahead and do that. But if you need to do this, if you need to wrap a piece of paper up and write the word front on it, then do that. Even on a test, go ahead and do that. Which end is north, which end is south? Left side, south or north? North. The magnetic field inside the coil points towards the north. Outside the coil would curl around here and point toward the south. So this magnetic field would cause the domains in this piece of steel or whatever to start aligning from south to north. One more, and then we'll move on to our new stuff here today. Here we got another piece of steel that's not magnetized. We got a solenoid that wraps around it. We got a battery over here. I don't know what that battery looks like. It's there. I just don't have it drawn. We're going to say that we got a north pole down here, south pole up here. Not because I stuck a magnet inside this wire, but because I stuck a piece of steel inside this wire that became magnetized due to the current in the wire. We just want to find out which way the current goes. Kind of working backwards here, right? We know the magnetic field goes from south to north inside the coil. Therefore, if we use the manipulative that I made yesterday, my thumb will point downwards. Thumb points down. Now, you still want to put your fingers on the word front on that manipulative. So thumb points down, turn your hand around however you do it so that your fingertips land on the word front. Don't worry about which way they're pointing. Just observe which way they're pointing. Whichever way they automatically point is the direction of the current in the front. So which way are my fingers pointing? They're pointing to the right in the front. That means the current will go around like this and then come around like this. All right, how do I draw my battery? Like this or like this? Option 1 or option 2? Chase? Option 1. Is he right? Yeah. If we had have drawn this, using conventional current, we would have gotten the exact same thing. It doesn't change anything, except that we would have had the current going the opposite direction. We would have used our right hand, but it still would have ultimately produced a battery that looked like this. Yeah. Yeah. The north end is not always at the positive of the battery. Okay. Okay, it's a good question. I'm glad you asked that. This was going to be my last example, but let me show you one more quick example here, okay? I want to draw it as close to identical as I can here, except for one thing. You see the difference between these two diagrams? Okay, we have battery set up the same way. It's all vertical, whatever. But you can see that the wire goes in front here. It goes behind right here. Now let's see what the polarity of this guy is, okay? The current is still going to go clockwise, like it did in the last one, except it's going to go around like this in the front, right? In order to maintain that clockwise nature. Let's take your little craft that you made yesterday. In the front, my fingertips have to point this time towards the left. My thumb is going to point upwards, which means that magnetic field goes this way, North Pole and South Pole. I wish that it was as simple as remembering, oh, the north end is always going to be by the positive terminal of the battery, but it isn't. Okay, there's, depending upon which way we have the battery, depending upon which way we have the wire, the scenarios for polarity are different. I think I figured out once there's 8 possibilities. Well, you could, I suppose, memorize the 8 possibilities, but it takes less time and it's more accurate, likely in the long run, to think about how to do it as opposed to memorizing all 8 possibilities. Guys, be comfortable with that? Ready to write a quiz tomorrow on that? Change this just a tiny little bit, actually. 1, 2, 3, 4, 5. 2, 3, 4, 5. Clearly, in these two, the polarity is opposite, right? And we just explained why the polarity is opposite. What else is different about them now? What else is different about these two magnets that were just produced? This magnet with the North Pole down here, and this magnet with the South Pole down here. What have I done to it by adding more coils to it? Have I changed the direction of anything? No, we haven't paid any attention to the number of coils at all, right? So what does that do if it doesn't change the direction? Christian? Yeah, it changes the strength of it, right? We talked about that a little bit earlier when we were going over one of the questions that we had for homework. The more loops you have, the stronger it's going to be, right? The other thing you could do to make it stronger is have a stronger battery. So instead of having a 1-cell battery that's, say, 1.5 volts, you got a 3-cell battery that's 4.5 volts. Both of those things are going to cause this to be a stronger magnet, a magnet with opposite polarity. Okay.